So in part one, last time we were just about to apply power to the Drake transceiver, the TR-3, and I think that this is a good opportunity to go over the circuit in the Drake and some of the design goals that came out of competition in the early 60s. The Drake, of course, had a huge competitor in the KWM2 by Collins, and Collins had a very particular architecture with that radio. Their idea was to make essentially a 455 kilohertz sideband generator and sideband receiver, and then mix that up to the various bands using a heterodyne method with a VFO, actually a PTO, a permeability tuned oscillator. And that way you could take that 455 kilohertz transceiver and move it right up the bands. Now Drake could have followed that architecture, and they could have done a dual conversion system like the Collins, but instead they decided to go a completely different direction. So we have to talk about the KWM2 because this represents the first practical transceiver that became available to amateurs that really was a high-class device. Collins put together a dual conversion transceiver, and by dual conversion I mean we've got a first IF and a second IF. The idea of a bandpass crystal-controlled converter front end, followed by a tunable first and then a mechanical filtered fixed second IF on both transmit and receive, and with shared oscillators, comprises a true transceiver architecture, and one associated primarily with Collins. Stability was essentially a combination of the PTO stability and the crystals in the band heterodyne converters. It was not long before others copied this basic dual conversion scheme, most notably Hallicrafters with the SR-150 around 1962, and Heathkit with the SB line in around 1965. Of course, Collins was using their patented mechanical filter, and they had a carrier oscillator system which allowed you to go from upper to lower sideband with two crystals. When we get into the Drake, however, Drake goes a completely different direction in that they wanted to accomplish 5 bands, giving you 80 through 10 meters, using a single conversion architecture. Single conversion puts a little more pressure on your VFO, PTO. You have to have absolute stability, and the way that they handled it with the Drake is they decided to do a heterodyne VFO. The Drake TR-3's concept of heterodyning is a little bit odd in that they don't even use it on 2 bands. On 80 meters and on 20 meters they use just the PTO itself to produce the tuning range. Now 80 and 20 are lower sideband for 80, upper sideband for 20. They do 9 megahertz minus the PTO for lower sideband on 80 meters, and they do 9 megahertz plus the PTO for upper sideband on 20 meters. Very clever. However, on 40 meters, 15, and the 3 10-meter bands, they do use heterodyne system. So you end up still requiring 5 crystals, but we're actually covering 7 bands. So in this very simple circuit, you can see that we have a 9 megahertz IF. That's something that will come up later in more modern transceivers. By using a high IF frequency rather than the 455 that Collins used, they can reduce the possibility of images and other spurious. So the Drake uses a simple architecture, but in some ways it's quite elegant. Now they did cut corners. Notice they have a single 9 megahertz carrier BFO frequency. For some reason they decided not to put a lower sideband, upper sideband crystal there. They decided just a single 9 megahertz carrier oscillator. That meant that they had to use 2 crystal filters, one crystal filter for lower sideband and one crystal filter for upper sideband. But altogether, we end up with a far simpler circuit than the Collins, and the quality and stability remains. So one artifact of not having an upper sideband, lower sideband carrier is that you have to do your upper sideband and lower sideband by fooling around with where you put the heterodyne oscillator for your mixer. So in some bands, you have to put it above the band. In some bands, you have to put it below the band. So this causes some confusion, and you'll see on the Drake dial that some of the bands tune as you're turning clockwise upward, and some tune upward counterclockwise. So you have to pay attention to your dial on the Drake to know which way you're tuning. We're about ready to apply 12 volts, 12 or 13 volts to the radio, and I'm going to do that with a power supply. And to bring it up slow, there's no high voltage involved here. All we're looking for is tubes to light. It looks to be about 5 amps is what this thing wants. Okay, she's lit up. Let's try this. Okay, upper lower sideband's working. So here we are, 50 watts. 50 watts just to light the radio up. See, I told you tubes were better. Okay, everybody gets very excited. This is the initial power on with a variac. Bias level has not been set for the finals. No antennas connected. I have got a protective cover over the final cage. I've just got it in the sideband position. And 80 meters. I've got the RF gain up full, the audio up somewhat. And let's just see what happens when we bring up the variac. Going to bring it up about a quarter. Let's keep going. Don't see any smoke yet. That's always a good sign. Starting to see some of the lamps light. That's good. Starting to hear a little humming out of the speaker. Oh, I hear some hiss. I hear some hissing. Okay. Yeah. Always a good sign. Now, when we have the bias set correctly, this should be at 0.1 right now. This is just an old military microphone that I found. It's wired right to PTT it, but the impedance of this military microphone is way too low for the radio. But it does key it properly, so that's nice. Now that I know it's somewhat happy, let's go through the manual. First we'll set the bias for the finals, make sure we get that set right, and then we will start the alignment. I think we have a working radio. Upper sideband, lower sideband, CW. Anyway, the TX this is a TX drive. I don't know what that's doing, but that's set all the way counterclockwise. So we got some work to do to get this thing aligned, but we've got a good start. So on the TR-3 alignment procedure that's in the manual, it's pretty well written. You can tell that it's well thought out. Some of the methods that they use to tune some of the double-tuned, lightly coupled bandpass type stages, it's a little bit tricky. They use a kind of an odd system of using some specified loads. Anything that you don't understand in the procedure, it's probably best to skip over. I say that because the radio is basically working, and the one you have will probably be in similar shape. There's very little that can go on with these cans. It's not like somebody's going in there and messing the whole radio up. Hopefully not, anyway. So if it ain't broke, don't fix it. And if you don't understand something, it's better not to do it than to go in there and mess with some adjustments and get the whole radio messed up. So looking at the alignment instructions, they talk about using WWV. We're going to need a VOM or a VTVM. One of our multimeters will work for that. And this alignment load, which is a 1000 ohm non-inductive resistor and a 1/2 watt in series with a 0.005 disc ceramic capacitor, that's just something that you can put on certain places to load the tune circuit. 52 ohm dummy load, we have that with a watt meter, so we don't need to use a meter with a cantenna with a diode detector or something like that. You can use a low value watt meter. Okay, very quick CW mode before we've even got anything aligned. We go to CW, hit the key. Okay, it looks like we're putting out about 60 watts. I'm not going to go crazy before I do an alignment, but yes, it's basically working. So the first thing we've done is adjusted the bias so that it's a resting current of 0.1 on the meter. And that was done according to the instructions of rotating the gain control clockwise and the transmit gain control, which is really the drive control, counterclockwise. Sideband switch to the counterclockwise position. Function switch to XCW. And we adjust the bias pot, which is up in the power supply, for reading of 0.1 on the plate amperes meter. So that's setting the Class AB bias for the finals. So the next step is to adjust the dial calibration. I couldn't get anything out of the calibrator. Thought it might be the crystal, but a small mistake on my part. When I took the tubes out, I got the 12BA6 and the OA2 regulator tubes swapped. Fortunately, there was no explosion or any problem, but you know, magically now the calibrator works, so we can do the rough dial calibration. The instructions say to disconnect the high voltage and the medium voltage at the partition. What partition? What are they talking about? Well, this is the partition here, and I want to show you where the high voltage is. High voltage is this feed right here. They've got some plastic around a choke, and that goes down through the chassis and up to the plate caps of the tubes. And the screen grid comes through this choke, and it gets split through 3 68K resistors to the screens. So the first thing we want to do is identify that they really are the high voltage and the medium voltage. And I'm going to do that by turning the radio on. And I'm going to bring the variac, which I have over here, up to about 25%. That should put, you know, at least 100 volts on the high voltage, so we can just tell that we've got high voltage there. Okay, there's 179 volts. That's the high voltage feed. And the screen grid should be a little lower. 71 volts. Okay, so we've identified we've got the high voltage and the medium voltage feeds to the finals. So let's turn that down. Let's turn this off. Let's let that discharge a little bit. And let's actually pull the plug out from the power supply. Okay, so we've removed the power supply plug completely. Let's check those points again. Okay, 200 millivolts. Just a few millivolts. Okay, I don't know if you can see it, but we have now removed both the high voltage and the medium voltage leads. So the feed-throughs are now disconnected. If we key the radio, turn up the drive, do whatever we want to do, the finals are not going to respond because they have no high voltage on them. Therefore, we're not going to burn anything out. So as we start the alignment procedure, I just wanted to point out that There was a rough spot in the chassis back here in this area, and I did rub that down a little bit and hit it with some of that copper paint just to make it look a little better back there, because it was pretty tough. These are marked okay, so we can work with that during the alignment. There's no need to mark up the radio anymore. And again, we've disconnected the high voltage from the final. So best thing, let it warm up for about an hour before you start to align the oscillator. So that'll be the first thing we do. So what we're seeing is that we're getting 0 beat, low in frequency. The crystal has drifted, and even though I can adjust the trimmer, I cannot raise the frequency on the 100 kilohertz enough to get back to 100 kilohertz. So I'm at 99.972. Now, some of you may say, who cares? You know, who cares that you're off 30 or 40 hertz? It doesn't really matter. But let's pretend that we do care. And what we're going to do is we're going to try to correct this by putting a capacitor in series with the crystal, and we'll try to raise that up just a touch. Okay, so let's look carefully down at the trimmer. As you can see, I've got the scope probe with just a few loops that are stuck around the calibrator tube. That's my pickup. I haven't had to attach anything, and I don't want to attach anything. I want to be very lightly coupled. Now that was where the trimmer was. It was maxed out. We've added the 680 picofarad cap in series with the crystal. Okay, so that was enough to get us to a point where we have 0 beat. I'm going to continue. And we have double tuning. So we have 2 tuning points on the trimmer. That tells us that we're pretty well centered. And we are now at 100 kilohertz on our calibrator. I know that was a lot of work, but that's how you get exactly there when the crystals have aged. In this case, the crystal aged lower in frequency, and we put a capacitor in series with it of 680 puff to bring us down. Now anything from probably 390 to 100 picofarad or 1000 picofarads probably would have gotten us there. Okay, I'm using the dribble method again to pick up some 9 megahertz energy, and I'm mixing that with the receiver, and then I'm just tuning the generator till I get 0 beat. And what I'm seeing is that we are somewhere around 250 hertz low in frequency on the 9 megahertz oscillator. 250 hertz. So 200 or 300 hertz off probably isn't going to upset the apple cart too much. But again, let's try to bring the 9 megahertz oscillator exactly on frequency. Also, this is a good time to test the theory that when you go into the CW position, that the oscillator is offset by about 1 kilohertz. So let's go to CW. Okay, we're now in the CW mode, and it has indeed lowered the frequency. So you get a situation where when you're transmitting on CW, you don't end up walking up the band because you keep tuning the guy to get 1 kilohertz, and he sees you move 1 kilohertz, so he moves 1 kilohertz, and then you move 1 kilohertz, and pretty much you're going right up the band. The TR-3 took care of that problem, unlike my NCX3. So let's hope the adjustment of the 9 megahertz is a little easier than the 100 kilohertz, where we actually had to add a capacitor. So first let's tune exactly to 9. Okay, that's pretty close. So now we're going to rock C130 and try to bring that tone to 0. Now that we have the 9 megahertz oscillator and the 100 kilohertz oscillator on frequency, the calibration points should start to make sense. And this is how you can check the PTO to see if the dial is good. Looks pretty darn good to me. So the next step is to peak the crystal oscillators. And there's this L1, L2, L3. Basically you adjust on different bands. You do this with the meter. You're maximizing a negative voltage on the test point. I'll show you where that test point is. Kind of hard to do because you've got to attach to the bottom of the rig, but you do the adjustment from the top. If you do it from the bottom, you have to use a completely non-metallic tool. So it probably is easier doing it from the top. And it does tune pretty fast. Let me get on L1 here. So the next section is adjusting the VFO output coupler, which is a double tune circuit right in the plate circuit of the VFO. It's an electron coupled oscillator, so you have to peak those coils. And the way they do it with the radio is they do it with the S meter, and that decouples you enough that you can adjust that coil without getting into too much trouble. Okay, so I've done the injection oscillator, or the injection level settings. I've done the injection level settings, and now I'm just going for noise on the IF transformers. Basically this is T11. Just going for maximum noise with the IF. Just run through the whole procedure. This radio really was pretty well aligned. I really haven't done anything radically different. I did notice that after the oscillator alignments, getting things on frequency, that the dial corrector on the front is now right about in the middle, which is really nice. I was concerned that the PTO might have, been way off with all the fooling around and cleaning I did with it, but okay, that pretty much completes the oscillators and the receiver portion. Now we have to hook up the high voltage and the medium voltage to the finals, and we get into the balanced modulator and the transmitter chain next. Now to do the transmit section, after we've connected the power, we have to make sure we connect the dummy load now. You have to have the 50 ohm dummy load on the transmitter just in case you transmit. You're going to need a PJ068 Collins style plug, which is the smaller diameter plug. Looks like a stereo plug, but it has a smaller diameter than the 1/4 inch that you're used to. Okay, I've got the Fillmore jack soldered onto this simple slide switch. That's going to go straight into the mic jack, and that's transmit and that's receive. So this is just a way to key the radio as we test. We're going to do something else with our high quality receiver that has an S meter. We're hooking it right to the output of the transmitter. There's still a dummy load, but I'm actually attaching the receiver right across the dummy load. We're not going to transmit into the receiver, but we have the transmitter in the single sideband mode, and we have it in transmit with no microphone, and we have the gain control turned all the way down. Okay? What we're looking at on the meter is the amount of carrier that's sneaking out the antenna. Now remember, we went through a carrier null procedure, but this receiver is more sensitive than that meter that we were using to try to null the carrier. So let's see what we can do with the receiver. So first let's play with the potentiometer. Let me try to get a little closer here. And I'll let you see the meter as I attempt to turn the nulling pot. So I'm reaching back. Okay, I got it down there a little bit. Now let's adjust the capacitor. Remember that was C1. That capacitor is C127. Now back to the pot. Now back to C127. Okay, so we have a pretty good null going now. I tuned it up on 80 meters, 2.7 megahertz lower sideband. We're in the sideband mode, but with no microphone and the gain turned totally down. And now we have nulled the carrier. So I was adjusting right here for the carrier null and the capacitor here. C127. I'm in the CW mode on the middle band in 10 meters. So that means I'm tuned to 28.8. I believe that would be a good spot to neutralize the transmitter. The first step is you have to resonate the transmitter for 10 meters. So, when we're in the receive mode, we're just peaking the noise. We go to CW, we have the key installed so we're not transmitting, and we're going to slowly bring up the drive till we see something on the meter. There we are, we have some power. So now we're just peaking the output, playing with the loading. That's all I wanted to do. So I'm going to show you a neutralization method that was taught to me about 20 years ago. It's called reverse neutralization. Now we know that transceivers and transmitters have an output connector, and that output connector is made usually to work into a 50 ohm load. Well, that's interesting because most signal generators that we have are designed to deliver power into a 50 ohm load. So why not put the generator into the transmitter's output port? Okay? So where I'm going with this is that if you make sure that the transmitter is in the transmit position but is not actually putting out any energy, and I'm guaranteeing that with this guy by disconnecting the high voltage and the medium voltage from the finals, and I'm being careful to keep the drive at 0, you can hook up to that port safely. Now I'm not quite sure if my generator is exactly 50 ohms, so I've actually put a 6 dB pad just before going into the port on the transceiver, just to guarantee that we have 50 ohms there. Next, I'm using a very sophisticated receiver that has an S meter. It's the Heathkit HR10. And all you do is attach that receiver to the plate of the driver tube, and that would be the grid of the finals. And I'm coupling with a 10 picofarad capacitor because we know there's going to be high voltage on that driver tube. So that becomes the output where I sample, and it goes right into the antenna port on the receiver. So we're going into the output of the transmitter and looking at the grid or the plate of the driver tube, which is the grid of the finals. We're going backwards. Now we peak the output tuning network of the transceiver just like we're transmitting. Matter of fact, I would suggest that you do the tuning and the loading before you even get this far. Peak everything up. Do the driver and the output network, get those all peaked up, then disconnect the voltage from the finals and start your test. So I peaked everything up backwards. Now all we're going to do is get a signal that basically gets you up into the top of the S meter. So you got a good signal. Now we are going to balance the bridge. That is, we're going to adjust the neutralization capacitor. Let me try to do this so you can see the meter. Oh, also we have to tune the receiver, obviously. Right, and the trimmer. Now go after the neutralization capacitor. Remember, we have high voltage here, but not on the final, so be careful. Let's start rocking that trimmer. Okay. We are now neutralized. No guesswork. No trying to make a meter match some other thing. And it's extremely safe. There's no doubt. We have balanced the bridge. I'm doing this on 10 meters, 29 megahertz. And this is a no fail, no fuss method of neutralization. The Drake uses the Brune neutralization scheme. Basically, a large capacitor is put between the bottom of the driver tank, but not so large that a neutralizing capacitor brought back from the plate circuit can't slightly raise that point above ground to form the bridge on the right. Now, of course, you can neutralize in the forward direction as well. Reciprocity says that you can neutralize the bridge with the power going forward or reverse. You can actually use the transmitter itself to neutralize the radio, but it's a little more dangerous because you're trying to get power out of the transmitter in a controlled way. So this is the IF neutralization. Because this is a true transceiver, there is feedback between the transmitter and the receiver. So if we were to turn up the RF gain a little bit and turn up the mic gain, hello 1 2, hello 1 2, hello 1 2, hello 1 2, we actually can get some feedback between the transmitter and receiver, even though we're still in the receive mode. So what we have to do is neutralize this by adjusting a capacitor. And they're saying that while talking into the microphone, increase the receiver gain until the speech can be heard from the speaker, and adjust 168 for minimum output from the speaker. So we're trying to get rid of this. Okay. The alignment process that I went through was not exhaustive. I'll take that back. It was pretty exhaustive. But I did not cover every single detail in the alignment. But I hope I covered the highlights and you got a flavor for what it's like to work with a fairly complex transceiver with a lot of adjustments. So we're going to have one more video, and that's basically buttoning up the radio. There is a couple little things I want to do to it before we button it up and show it off. But in part 3, the radio is ready for delivery.
Calling CQ, CQ, CQ. Calling CQ, CQ, CQ. Mike 0, Charlie, Golf, Foxtrot calling, CQ, CQ, CQ. Mike 0, Charlie, Golf, Foxtrot.